All right. Why did my screen lock when that was happening? Let's get that unlocked here. All right. Hello and welcome to the Off by One security stream. For whatever reason, I started the countdown timer, which I think makes things too suspenseful now. But my computer decided to lock at that exact moment, and there was no reason for it to do so. So a little suspicious, but that's fine. So November 1st, happy Halloween, everyone who celebrated that. Hopefully did something fun last night. This is our first stream of November. I've got a few streams coming up planned. I'll mention those in a little bit. This week we've got Alexandre Becholey. I know I don't say your name properly, but I try. It's a much cooler name than mine. If you want to say hello and introduce yourself, that'd be great.
Yeah, hello. You can call me Alex. Perfectly fine. I'm based in Europe, Switzerland. I am an independent security researcher. Been doing that for 4 years. My focus nowadays is more on Android, kernel land, and baseband. Before that, I was working with Sophos on the West Coast in Vancouver, focusing on AV bypass, endpoint protection bypass, finding weaknesses. Also some research. I found a vulnerability in the secure kernel of Windows while working there, which was a lot of fun. And before that, I spent almost 5 years as a pen tester back in Switzerland. So I just touch and go to Canada and back, and now, yeah.
Okay, that's cool. Go ahead, sorry.
And yeah, before that, just a year and a half of sysadmin in a bank, and that's it.
I didn't know you found a secure kernel bug. Can you talk about that one, or is that something you can't talk about yet?
Oh yeah, no, I can. It's super old. It was back in 2019,
Okay.
early 2019 or something. Basically, I was researching Hyper-V, so the Microsoft hypervisor, and the virtualization-based security VBS that they're using it for. That hypervisor allowed them to sort of isolate stuff on your system, so that if your system is compromised, you don't have access to all the juicy stuff like credential guard is putting the cached credentials somewhere else in an isolated memory space. And in that isolated environment, you have that secure kernel. It's a super minimal kernel, and it relies on the anti-kernel, so the normal kernel, to do most of what's needed, like file access and whatnot. And those two kernels need a way to communicate. So I found a vulnerability from the kernel land to get an arbitrary write in the secure kernel. So
nice.
Isolated memory part.
Yeah, I've had a couple people on talking about how to debug the secure kernel and Hyper-V with like JTAG or another way. And so I noticed a lot of interest in looking at the brokerage going on between the kernel and the secure kernel with the isolated user mode processes. A lot of interest in that attack surface, but it's pretty well locked down. But I was talking to Dave Weston at Hackfest earlier this week on Monday. He did our keynote, and he was saying, "Oh, there's all kinds of bugs there." So apparently, there's plenty to go and still find out there if people want to.
Yeah, the funny part was that it was my early days into Windows research. Before that, I was mostly on Linux. So basically, I was debugging Hyper-V and the secure kernel with GDB. I was rolling all that into KVM with QEMU, and with QEMU, you can attach GDB in it. Now, that was 4 months debugging, because when you interrupt, you never know where you are. You can be in user land, you can be in kernel land, you can be in Hyper-V. That was spicy.
Wow.
Now you have better tooling for that, I guess.
Sometimes it's when you're first getting into a particular area you haven't looked, where you stumble upon something that other people wouldn't find just because of the way you're approaching it. So.
Yeah.
Whenever
go on.
Oh, sorry. I was going to say, so for folks listening either live or after the fact on YouTube, Alexandre is helping me with a section in the SEC760 course. So we just completed an update, and he wrote a section on browser exploitation in Chrome on Linux. And I thought that, I did a couple of browser exploitation videos in the past, but those were from like IE11, for example. Obviously, this is something newer, so I thought it'd be interesting for everyone here who wants to learn a little bit more about getting into JavaScript and V8 and kind of some of the prerequisite knowledge you need to have when going in and looking for vulnerabilities or exploiting a browser in modern times. So I asked him to come on and present a section. So I think we've got about 30 or so slides that he's going to go through, and then also do a little bit of demonstration. We won't obviously be going all the way through and finding the vulnerability and weaponizing an exploit. That would take hours and hours. And maybe we'll do another one if this one's popular and people want to see it. We can do another one that focuses on the next step after this. But I think this one will be a good one on getting folks up to speed, especially because V8 is such a beast. A lot of people are just like, I don't want to touch V8 because there's a lot you need to learn. And but I remember there was a paper from Exodus Intelligence that came out a couple months ago, I think now, and it was a long one. It was a pretty heavy read, and you can really see all the work that needs to be put in to find and weaponize and exploit a modern vulnerability when V8 is related. And then of course you've got the sandboxing and everything else around it. So a lot of people have moved away from browser exploitation. If you've heard me lecture before, you've heard me say many times that back in 2014, that's 10 years ago now, it was so easy compared to what it is now. But that's just the way things go. And even the techniques shown in any course out there, or any technique that's disclosed in a paper, and even some of the techniques that Alexandre is going to talk about, they get fixed, right? We find a technique, a method to do something. You can use it for a little while, for a short period, and then it gets fixed. And then we have to find another way to get code execution, or to get some of these, make these primitives exploitable. So I guess you have a lot to cover. So I was thinking, let's just jump in. If you guys have questions, anybody watching has a question, go ahead and post it up. And if it's related to what is up on the screen, I'll probably interject and ask the question. Otherwise, we can hold off questions till the end. But as always, I definitely happy for you guys to post up questions if you have them. So I'll just pass it over to you, and we'll get started, and we'll just kind of make it interactive as things get going here.
Yeah. So the Chrome module is split into 4 sections. There is an introduction to JavaScript and V8. The goal of that section is to give the required knowledge to understand the vulnerability and to be able to exploit it. It's not a 101 class on JavaScript, and it's not a full cover of the V8 internals. That would take days. Here just had an hour to do so. So yeah, keep that in mind.
Yeah, I've seen a class that was 2 days, 2 days on nothing but V8.
Yeah, so yeah, usually you have your browser exploitation class. It's 4 days. It's 2 days on V8, 2 days on JavaScript core for WebKit. But yeah, so that's the focus of the stream today. Hopefully we'll have a sneak peek at the second section, which is identifying the vulnerability. Try to find a bug, exploit it to trigger a type confusion, actually. And then the rest of the 2 sections is building primitives to read, write the memory, and finally get code execution that way.
Yeah, I think the term shellcode smuggling, and a lot of people might not be familiar with that, and I don't think you're going to be covering that today, but if you want to give a little definition as to what shellcode smuggling is, that'd be great.
Yeah, so okay, can I do that when I talk about the heap layout of the...
Absolutely.
Yeah, I will come back to that later.
Cool.
So yeah, we have some objectives here is to understand to understand a bit of JavaScript, some V8 internals that is needed for the exploitation, and yeah. So V8, what is it? It's the JavaScript engine of Chrome, or any project based on Chromium. So we'll find it on web browser like Chromium, Chrome obviously, Opera. You will find it also on the new Edge, so Edge Chromium. The older Edge, the original version of Edge was on using Chakra Core, which was Microsoft's own JavaScript engine. Now they moved away from that and are using Chromium as the base for the Edge browser. The initial release was in 2008. I say it's roughly 2 million lines of code. It's hard to measure. because it's part C++ and part Torque. Torque is a language that is, let's say, easier to write with. Let's say JavaScript developers are used to a specific syntax, and Torque is quite similar to that. And then that Torque files are converted to C++ at compile time. V8 in itself, you can compile it as a standalone binary so that you can play with it. And that binary is called D8. It's great for research. You don't have that huge web browser with all the memory that's needed and all memory footprint and big binaries. Just have that part that is of interest, which is the JavaScript engine. You can invoke D8 with some options. There are 3 options that we use here. And then you can also specify a path to a JavaScript script. The first option that is quite useful is the allow natives syntax that will enable V8 internal functions that you can use to introspect what's happening. There are many functions to, for instance, if you're interested into the JIT compiler, just-in-time compiler, turbofan, it will show stages of that compiler, a lot of useful things for research. Obviously, a web browser doesn't allow that. It's only for research. We'll see a couple functions that are useful when we play with D8. The second one, I will not mention it now. It's, well, yes, okay. Basically, when new APIs are introduced in a web browser, so let's say JavaScript API, are introduced to a JavaScript engine, they are not enabled by default at first. You have to enable them. So here, with that second option, harmony set methods, we enable the harmony method for sets. Basically, it's to allow developers to play with them. And then when they are ready, they are enabled by default. That vulnerability was found when those libraries were in those early stages. So that's why we need to enable them to be able to execute. The third one, the shell, if you're familiar with Python you can invoke a script. So Python, then pass to your script. And then Python will execute your script, and then you are back to your shell. You can use the -i option on Python to keep the interactive shell. So it executes the script, and then you have the interactive shell. This is exactly the same here for D8. If you execute D8 with the script, it will execute the script and then exit, and you back to your bash. If you specify the --shell option, you will, after the execution of the script, you will end up in the interactive interpreter. We will see all that in demonstrations. If you see the command line, there is that RL wrap. That's the read line wrapper. Because D8 is not super, it's a bit raw, it's a bit crude. You don't have any history. You cannot use the arrow keys to go back in the history, or even left, right to edit the current command. You will see those strange characters being printed out instead. Here you can use RL wrap to wrap D8 with the read line, and then you can use the arrow keys. You can search in the history for previous commands you have entered, so it's super nice for to play with D8 that way. You package in many Linux distributions, and yes, it's really useful. It has 2 drawbacks. The first one is that sometimes it might hide a crash message or give you just not all in the, everything that a normal crash would output on the screen. And the second one is, as it will redirect input and output on D8, it might break some shellcodes. So when you are testing your shellcode, be sure that you are not using RL wrap for that. Usually, JavaScript is embedded into a HTML page. You can have inline JavaScript in between those 2 scripts tag, or you can have a remote script that is downloaded by the browser where you specify the path to the script that way. Here, we will not do any HTML as we are just focusing on V8 and JavaScript. So let's have a look at my virtual machine. Is the font big enough for you guys?
Yep, looks good for now. If it looks too small for you guys online, let us know and we'll increase the font.
So I think I have a script that is called hello world, just console.log hello world. So my D8 is here, and I can specify the path to that script. And as you can see, outputs hello world, and then I back into my shell. Here, if I specify that -- shell, now you can see hello world, my script is executed, and then I am on D8. And here I can say let A equal a new set. And if I want to use the arrow keys, as you can see, doesn't really work really well. So that's why we want to use RL wrap for that. You can also just call D8, and then you can do a console.log hello off by one chat. And yeah, you also always have the return value of the function here. You will see all those undefined. This is not something to worry about. Just ignore that for now. In JavaScript is dynamically typed. It means that a variable can hold different types through its lifetime. A variable that is just defined like so without any initialization, it will be of the undefined type. You can specify a string like here, SEC760. You can specify a number, then it's a number, or just an empty object. Most things in JavaScript are, in V8, in JavaScript are objects, except for the null type, undefined, number, and strings, which are sort of native types and not a JS object. JavaScript is also weakly typed, and that's super weird. Let's have a look on the here. I will use RL wrap for that because it's it will be a better user experience. So the string 1 divided by 2, well, 0.5 makes sense, right? Now the string 1 plus 2, well, it's the string 12, which is
How could
weird.
there ever be confusion with this, right?
I mean, yeah, it's weird. I'm not a JavaScript developer. I guess they will say, oh, that's normal, I guess, but not for me. Say, oh, let's try to concatenate two arrays. Well, not really. It's going to be a string and a weird one. You can take an empty object and you add an empty string. Okay, return 0 for some reason. Or an empty string plus an object. Well, this time it's an object. So, well, it's the string object. So, yeah, it's weird. If you're interested, there is that website jsisweird.com, and you can see many, many more JavaScript weirdness there. Okay, there are many ways of defining a function. Those 5 techniques here will do exactly the same. So you can have functions, and then name of function, maybe arguments, and then the body of the function. Here we are returning x times x, so the square of x, basically. You can create a variable square2, which is a function, one argument, x, and same body. And you can use those those syntax as well, where you say, okay, square3 is a function that takes one argument, and here you have the same body. Or even smaller that way. And here we can see that functions are also objects in JavaScript. So yeah, use the one that you want. Sometimes you might want to use those 4 techniques here. If you're redefining an existing function, you can use those techniques. Yeah, variable declaration. You see me use var or let, and they have a subtle difference. Var is, I would say, don't use it. I'm sort of against using var because, yeah, let's say you have your function that is called something. First, it initializes a variable a to 1. Then you have a block. It's just changing the scope here. It could be inside an if statement, a loop, or something else. And you declare that var a equal to, and then you log a, and then outside of that block, you log again a. You might say, okay, so that here should output 2, and that here should output 1, because that's this a, and that a should be this one, right? Well, not really, because var can hoist or steal that variable. And basically, when you do the a equal to, it's the same variable. So as you can see here, it's twice 2 that are output on the screen. Quite confusing as well. That's why I always say to use let. And that's the behavior that, well, in my case, I would expect, is that those 2 a variables are different variables because of the scope. And here, oh, it should, sorry, it's a typo. It should be 2 and 1. My bad. Should fix that. Okay. Chat is awfully quiet. Okay, we can play with array a little bit. Let a equal, let's say, an array with 1, 2, 2, 3, 4, and we can get a length. So an array is a special object that has a length. So yeah, 4 elements in that array. You can add an element at some arbitrary index. Okay. Now a.length 1001. Yeah, makes sense. The length can be modified. So if I, for instance, say, okay, now the length is 3, well, a now is only 1 to 3. So you can truncate an array that way. Numbers. We have what we call SMI, small integers, and these ones are represented using 31 bits. After that, if you need a value that needs more bits for representation, it will use float in the backend. In JavaScript, it's not possible to represent 64-bit values natively. You could use a big int object for that, but a big int is an object. And when we do exploitation and we want to place specific values or data on the in the memory, we cannot really use that. And we will use doubles for that. Yeah, arrays of doubles, because they are nice. We'll see later on why. But yeah, that's a limitation of JavaScript, is that way. And we'll see why SMI are only use 31 bits and not 32. when we talk about pointer tagging. In JavaScript, we have what we call a typed arrays. Here, the buffer is, let's say, a backing storage that will be used for 2 other arrays. So I create a backing storage of 8 bytes, and that will be the buffer. Then I use that buffer to create 2 arrays, the float array and the big int array. Both arrays will use the same backing storage. So whenever I set something in one of the array, it will be seen from the other array as well. So it's a really nice way to convert between a integer to a float. Because in your code, when you are writing pointers or specific values, well, you don't want to write float because it's weird. You want to use your hexadecimal. Here we can see to specify a big int, we use that n at the end of the value here to say it's a big int. So yeah, that 41, 41, 41, etc. Here we can see the float representation or the double representation, 64-bit float. And the other way around, 1.1, here we have the big int representation in decimal. You can also use some converter. For instance, Python is perfectly fine for that. You can create 2 functions, double to hex or hex to double, and you can reuse that as you want. There is converters online. If you search on your search engine for a floating to hex converter, you will usually you will find at gregstoll.com website where you have that. The first part is for 32-bit, and the second part here is for 64-bit. And here we have exactly the same values, 41, 41, 41, and we have that float representation down here. Okay. The vulnerability we are interested in that section is on sets. And well, let's play with sets. I will start fresh. Let A equal new set, just an empty set. And then I can add element. So for instance, I can create a for loop from 0 to, let's say, 64 element, I plus plus, then the body of the loop, a dot add, use the add function on the set to add an element to it. And here, yeah, I have my set. I can get the iterator on that set. For instance, iter equal a dot keys. And now I can iterate on all those elements, etc., etc. Here I get the iterator using a function on that object. In the background, what it does is basically using a symbol on an object. So you can also get the iterator using the symbol iterator. And basically now you can do the same on this one. Yeah. You can also delete element. Let's say delete the first 16 elements. A dot delete. You can have the size. A set has a size. Okay. We have what we call monkey patching, or we can overload functions in JavaScript. Allow me to create a new set. Let b equal new set. And for this one, I will overwrite the b dot keys function. I will say it's a function, doesn't take any arguments, and it will, let's say, console.log b.keys was called, and then I need to return the actual iterator. So symbol and if I don't have any typo, that should work. So obviously a.keys has not been modified. So this one is still the original one. But if I call the b.keys now, you see console.log exactly. So you can, yeah, what we would call monkey patch or overload a function that way. So here we are just modifying the function of a specific object. Let's see. Yeah, basically just that. Okay, that's about it for JavaScript. Just everything that needs to be known to be able to exploit that vulnerability. V8 has what we call a heap sandbox. Sometimes you will find it being called a Uber cage. It's a 4 gig memory region that is 4 gigabyte aligned. It's reserved. It means that not all pages in that memory regions might be allocated. You might have holes in between and some chunks of memory regions that are allocated. At the beginning, you always have that heap header. And as now we are using a 4 gig and just that 4 gig memory region, and it is 4 gigabytes aligned, it means that to reference any bytes inside that region, we only need 32 bits. So we can compress the pointer and totally discard the 32 most significant bits of an address. As it's 4 gig aligned, the least significant bit of the base address will always be 0. And the rest, the 32 most significant bit, will be the heap base address. And you can use those 32 least significant bits as offset inside that region, and therefore just store those offset or compressed pointer in there. So you basically gain, you reduce the amount of space needed to store pointers by 2. Make sense?
Yep.
Shellcode smuggling. So it also means that whenever we are, let's say you have a primitive, you can overwrite a pointer, maybe somewhere here. You cannot reference anything outside of that memory region. It's also why it's a cage, because you can not go outside of that heap sandbox. But we can make the engine allocate memory for different kind of things, like WebAssembly. WebAssembly, it's we will not touch on that, so it's basically part of the last section. But WebAssembly is sort of a portable binary format that should allow near hardware performance in a web browser. So you sort of have some WebAssembly binary code. You can see it as some bytecodes that is then just in time compiled by the engine before execution. And that code is placed in a read-write execute memory region, but we don't have access to that region. And the shellcode smuggling or instruction smuggling that Steve just mentioned at the beginning is we can control a few things that are placed on that memory region. For instance, we can create a WebAssembly code that will just declare some floats. and floats, 64-bit floats. And inside those 64-bit floats, we can smuggle some assembly opcodes. And at the end, we use a short jump that needs just 2 bytes. So we have 8-byte floats. On these 8 bytes, we can use 6 bytes for instructions. And then the last 2 bytes will jump to the next float. And we just jump from floats to floats to execute a simple shellcode. That will basically be a stager that will copy over your big shellcode somewhere else. So that's the technique, shellcode smuggling. You can do something similar with just-in-time compilation, so JIT. You can create a JavaScript function that declares floats. That way you force the engine to JIT it, as we say. If you call it a certain amount of time, the just-in-time compiler will trigger and say, oh, that function is used a lot. I will compile a version for it so that it will be faster for execution. Okay. Steve, that was, yeah, I guess. No questions.
No, everybody's on listen mode. It's all good.
Business as usual. Okay. So we have those offset or small pointers in memory, and we might also have some values. And how is V8 able to differentiate between the two? Each object or values on the heap is 4 bytes aligned. Even if it's an 8-byte value, a 64-bit float, it can be 4 bytes aligned. So it means that the least 2 significant bit of a pointer will always be 0. And it allows the engine to use those 2 bits as flags, for instance. And V8 will cut the pointer in 2. So we only have the 32 least significant bit, as you can see down here. Whoops. And then the last part, it will tag it with 1 to say that's a pointer. Okay. So now, okay, I have my SMI, my small integer. So if I want to store 1, what happens? Because, yeah, 1 is the bit 1. We have a problem here. So that's why we only use 31-bit. The value is shifted left by 1. So we have let's say shift by 1 to create that 0 at the end. So whenever you see a value that is even in memory, maybe you see a 2. You need to remember that you need to shift it right by 1, which is basically divide by 2, to find the actual value. So that's some weirdness on V8. We have pointer tagging, so pointers have that bit 1 set. Obviously, V8 will, when it will access an object, it will untag, so mask that bit off, and add the base address of the heap to get the actual pointer to get to that object. Let's see that in action. My virtual machine.
You'd think that happening over and over again constantly would have some level of overhead with the constant shift instruction.
There is a the V8 developers talks about it when they introduced the pointer tagging, and they had some ideas on how to make it faster. And basically, the dumb method was the fastest because branch prediction and whatnot. Yeah.
Yeah. Right.
But I mean, it's JavaScript is not the fastest language, anyways. So yeah, you already have a performance penalty here, and here we save a lot of memory by doing that because almost everything is an object except for those number, string, undefined, null, that I talked about before. So let's debug JavaScript. gdb-q for quiet, out, release D8. I have Jeff installed here. I can show you. And I also have a GDB init that is provided when you compile G8. It will create that GDB init, and it has a few helper functions that we can have a look at them later on. So now here I am. I have loaded the binary into GDB, and I can run it. Here I cannot use RL wrap, but I can specify arguments. Also maybe a script here. It will run it, starting program, and then as you can see, I have my interpreter. Console.log, hey GDB. Okay, I can Ctrl-C to interrupt and get control. Or I can attach to a running D8. So, wait, no, sorry. I need my D8 here, RL, here I can use RL wrap. I need to be in V8, RL wrap, out, D8. Okay. And now, if I specify an argument here, it will be a PID, so that GDB can automatically attach to it. If you only have one V8 running, you can just pgrep D8, and it will pgrep will basically return the PID, the process ID, and GDB will automatically attach to it that way. Okay, and I can continue. Okay, just be sure I don't lose track. Yeah, pgrep, blah, blah, blah. Yes. Okay. Allow me to create those. Can I search? Ctrl-R, set, yes. Let's overload that keys, equal new function. And this time I want to system break. Oops, forgot about that. Those native functions, internal function of V8, all start with a %. And B, symbol, iterator. And if there is no typo, that should...
You're missing a close parenthesis after system break.
Oh. Yeah, that was a curly brace here.
Or that.
And that should be good. Yes. So now when I call b.keys, that system break will trigger. And system break will just generate a breakpoint. So it's nice, a nice way to make the program stop at specific location in the code. And here you can see breakpoint somewhere, seek trap, trace breakpoint trap, and I have control. That version of D8 I compiled has some symbols. It doesn't have all the symbols with because that would be like a huge binary and takes a long time to load. But yeah, here we have the stack trace with the nice function names, which is good enough for what we want to do. Okay, continue. The second and the function that you might use the most is debug print. And you as an argument, you specify the name of an object, and it will give you a lot of good information about that object. First, you have the pointer here, and that's quite convenient because you can see it's a tagged pointer. It has the offset here and also the base address of the heap here. Okay, we can see some information. The map allows V8 to understand how to interpret that object. It will tell it, oh, it's a holy element, and then you have that map down here. You can at first you can safely ignore that. We might have some prototypes. Here we have a that's the default element, empty element when you don't have any elements or in here. We have a table, so this is where the elements of that, or the values that are stored in that set, will be located. It's inside the table. And then the properties. Let's have a look at that in GDB now. I will break with Ctrl+C, and x/4wx, that address, it's tagged, so I always have to untag it. So -1 is good enough to remove the tag here. And you can see, always in a JavaScript object, the first pointer will be the map. You see that 19B019, that's the map here. Then we have 4CA91, that's the properties. Then 6A5, that must be the elements. And finally, 4A861, that's the table. Let's have a look at the table. I can use that pointer and add the base heap address, or just take the full pointer here. And remember, it's tagged. Allow me to output a bit more than just 12. Yes, and we can see a few things inside it. What am I looking at? Yeah, the size is, yeah, obviously there is no size. It's empty for now. Let me see. I think I'm going a bit too far. Yeah, all pointers are tagged. Need to use the tag point. Oh yeah, job. So that's the internal function. You can list them with apropos V8, and you have all the functions, well, commands that are added to GDB by that special script that was created at compile time. And the job is to print a JavaScript object. So job, you need to use the tag pointer. So let's use that pointer up here. And you will see it's weird because it will output into the console. So if you are attached to D8, it will output in the console here. If you run D8 from within GDB, it will output it here, just after it. But it's basically the same, pretty much the same information that you have with debug print. Okay, that I think I've just shown. Okay, let's create an array. Oh, no, let's create a set with 3 values and see that in memory. Continue. Let b equal new set 0x41, 0x42, 0x43. Oh, okay, yes, B was already declared. C. back to GDB with that address for WX and -1 to untag it. And we can do the same with the table here. And we see 6 here now. On the empty set, it was 0. So that's the size. Remember, 6 is a value. It's an even data, let's say, in the memory. So we need to divide it by 2, and that's 3. So that's the value 3 stored in memory, obviously shifted left by 1. So yeah, we have 3 elements inside that object. You might find them if you look at it, and also they are these are SMI, so they are shifted left by 1. So we have the 41 here, the 42 here, and the 43 here, for instance. Let's have a look at arrays now. I will start fresh. Up. Whoops, that was too many Control D. CD V8. Okay, let R equal 1, 2, 3, 4. Okay. Debug. Print R. And of course, I need to reattach here. Where are you? Debug print array x/4wx, the address -1. We also have the map, and where are you? Elements. Why don't I see the elements? Oh, no, it's here. My bad. So, elements. And we go x/12wx -1, and we can see the 1, the 2, the 3, and the 4. Again, values, they are multiplied by 2 or shifted left by 1. You can do the same with floats. Let R2 equal 1.1, 2.2, and 3.3. That's good. And I will take the pointer back into GDB. -1. We have the table. Forcing A9, and I need a bit more. And you can see usually when you create an array that way, the data are stored right above. That's not always the case, but usually. So that's my array, GS array object. And the elements here point just above it, right here. And I have my 1.1, 2.2, and 3.3. So as you can see, the arrays of 64-bit floats are super nice because, as you can see here, I can control quite a bit of memory.
Yep.
So that's why we use float for that, and arrays, especially arrays of float, because they are stored next to each other's. Yeah, so the goal now, the students usually would play with D8 and do that and understand what's happening. What I want to show you is something quite specific with the sets. I will start fresh just to avoid any just to play nice with the demogod, so that I don't see any weird things going on. So let A equal new set, empty set for let I equal 0, I smaller than 664, I plus plus. Okay, let's do it that way. Console log I a dot add I, and we will debug print A. It's gonna be quite a lot of output here, but yeah. Okay, so 0 to 63 sounds correct. Yes, right here. So we add the first element, so 0, and the pointer of the table is this one. I will just paste it into my GDB so that we can keep track of it. Okay, now I add one, table doesn't change, but when I add the fifth element here, the table has changed. You see, the pointer is not the same.
Why is it doing that?
Now, because the set, the original empty set, only has space for 4 elements. Then you can compare again, and spoiler alerts on the 9th element, so 8 here. The table pointer also has changed. So the first table had room for 4 elements, the second one had room for 8 elements. Okay, fast forward to the 17th here, and I guess you can see a pattern. So that was for 4, that was for 8, that was for 16, and this one, there's a good chance that for 32. So fast forward to, we can see that normally 41 should be the same, 5C, 6E5, yes, and then that's 32, but as we are starting from 0, that's element 33, 5C839.
Yep.
And yeah, here we still are in the same table, because 64, it has room for 64, but basically powers of 2 starting from 4 is what we are looking at here. I will just save those right here, and we'll have a look at GDB, what's there. Should be attached. Yes.
What is a holy variant?
Great question. Something we don't really talk about, but an array, when you add element one after the other, it will be a packed element.
Yep.
A packed array. If you remember at the very beginning of the introduction, I had an array with like 4 elements, and that I added that value 1000 at index 1000. Remember?
Yep.
The thing is, the engine will not allocate a huge array for all those values, because technically I only need to store 5 of them, 1, 2, 3, 4, and 1000. So it will create what they call a hole, and sort of, yeah, save space with that hole.
Yeah, interesting V8 thing. Yeah.
Yep. Back to my table. So this is the table of a set. I will not look at the set, but just the tables and just the four first words. So this one, the second table, wait, something weird. I shouldn't have called the demoded. What is going on? Oh, of course, pointer tagging. Yeah, obviously. Yeah, that's more like it. Pointer tagging. I will just clear the mess. Pointer tagging. You will do that error many times. And then, especially during demonstrations. Here, I guess that's the 4 of them. So, what do we see? I told you that, quickly showed you that the third element here should be the size. So here, quickly, my favorite calculator, Python, 0x80. Remember, it's a value. We need to shift it back by 1 or divide it by 2. And that's indeed 64 elements inside that table here. So the final table here has 64 elements inside. But what you can see, the previous tables have a pointer instead of a size. And it points to the next table, 4C5B1, 4C5B1, 4C615, 4C615,
Yep.
4C6E5. I guess I missed one. Yeah, I missed this one in the middle. So yeah, and then this one we have the pointer to the last one. Sorry about that. Just missed one. So that's an interesting behavior of V8. Okay. I guess do we have like a few minutes to sneak peek the vulnerability?
Yeah, sounds good.
So, what is happening? Okay. So yes, that was basically just that.
Cool.
So we'll have a look at the vulnerability. It's in the symmetric difference. That's a function on sets. A great resource for JavaScript is the Mozilla Developer Network. And you can see that the symmetric difference method of set instance, blah, blah, blah. Basically, you have two sets, A and B, and it returns elements that are not in both sets. So elements that are in A but not in B, and elements that are in B but not in A. That's the blue area that I show here. That vulnerability was present in V8 when that function was not enabled by default. That's why we need to invoke D8 with that harmony set method to enable that API. The source code is in the set symmetric difference.tq, so that's Torque. And I've just commented out comments and empty lines. The receiver, so that's the code, and the next slide is basically explaining line by line what is happening. So let's have a look at that instead. I have a set A and a set B, and I want to create a symmetric difference between the two and store that in the new set S. In the code, the receiver is A. Other is B. So if we go back here, receiver is A. So, you know, with the dynamic typing and whatnot, the code will ensure that we are working with a GS set object. So that's why we have that cast on line 15. So that O is basically the set A. It's a bit more relaxed on the argument. So the B set, here we create we get the set record for that object and create that other rec variable. Then on line 22, we save the pointer of the table of A. You see here, O.table. Here we save that table, that pointer here. Then on line 25 and 26, we get the key iterator, the keys iterator of B, other rec. And finally, we clone the table of A. And this will be used for the result. Basically what is used as the table for the set S here, you see? So we cast, we don't really care about that, but we save the pointer to the table of A on line 22. We, in fact, execute the keys method on B to get its key iterator. And we clone the table of A. Is something wrong in that order of operation? What do you think? You see, that reference on A is saved but not directly used. In between, when we save that pointer and we clone it, we execute that b.keys here. And we've seen that with monkey patching, we can override that function and basically execute some JavaScript code there. And that's bad. The fix to the vulnerability is to basically revert the order of these two lines. And that will fix it. So I save a pointer. I execute the b.keys function that I can modify. And here I am able to execute arbitrary JavaScript code. And then that table is cloned. We've seen that tables can change, right? When we add a certain amount of objects. So let's try to overload that b.keys function so that the table of A changes. And here we're keeping the previous table. And yeah, let's see what happens. Let's start fresh again. Oh, yeah, sorry about that. The muscle memory, I guess. My bash, there is a thing, when I Control D and I bash, it will say no, use logout, so that this doesn't happen. That's something I added to my bash RC. So I'll wrap out D8, allow natives, that's a plural syntax, and harmony set methods. Let's try that way. Okay, let A equal a new set for. That's why our wrap is super nice, because you can reuse and you can go around and modify your code. Okay, so now I have 64 elements in A. Let B equal new set. Okay, b.keys equal hop, a new function. I will add, remember, 64. I'm at the limit of the size that the capacity of that table. So now if I add another element here, that table should change. And I need to return the actual iterator, symbol.iterator. Blah, blah, blah. We should be good. So that function is redefined, but has not been executed yet. Or what I can do is just for the, if you want to debug, you can have a, so that you know I'm not selling you snake oil here. B.keys code. And yeah, we should be good. So debug print A, pointer to the table. Let's go into GDB x/4 wx -1 this time. Yeah, 64 elements. Cool. Let's continue. Oops, continue. And now let's do that symmetric difference. S equal a dot symmetric. I'm sure there is a typo. What is it again? Yeah, uppercase D, symmetric difference. Symmetric difference on B. And you see, B, that key is called. Cool. Debug print A. Table has indeed changed. If I go back in my debugger and I print the table, you see that I have the pointer 5D55D, which is indeed the pointer to the new one. Okay, I created a new set. Okay. So let's have a look at that set. Table 4DA85. Let's have a look at that table now. Ha! We have a set, and this set doesn't have a value for its size, it has a pointer. Let something equal s.size. Let's have a look. Print something. We don't really know what it is, right?
Nice.
And yeah, you have your stack trace. So that's the type confusion. And basically from there, we try to get control of that pointer, move it around, place it on an array, and we create a fake object with those floats, and use the fake array to basically build the read and write primitives.
So this is an arbitrary out of bounds right then, right?
It's more of a type confusion because you have that pointer.
Well, yeah, type confusion, but leading to an out of bounds right.
Well, you will move it to place it somewhere that you control. You will create a fake object and use that fake object a fake array, because arrays are easy to build manually, and you can then read and write using the array anywhere in memory. Yeah. Well, in the heap sandbox, in the upper cage.
Yeah, it's so nice to be able to do this in a headless manner as well, instead of going through the browser all the time.
I mean, that's why D8 is super nice. It's easy. Well, yeah, easy. Cool. In a certain way. Cool. Yeah. I guess that's me.
Yeah, it's a nice bug. Thanks for walking us through it. I mean, definitely the JavaScript in the beginning and the V8, if you haven't played around with that, it's just like you said, it's a vast attack surface and just focused on the things specific to this bug, which is understanding something like this one is a great way to then, of course, go and search for new related ones. This one was earlier this year. I think this particular one was disclosed, right?
If I'm not mistaken, it was fixed, disclosed to the Chrome team on December 2023. But the thing is, there is always that period where those bug reports are hidden from the public. I think it's like 3 months, and then they get public after that. So publicly, let's say March this year,
Yeah. Cool. Well, if anyone has any questions, we're going to wrap it up here soon. So get them posted. I can imagine you've definitely got some. So take advantage of the fact. We're not going to continue on, of course, in this session. We've already been going for an hour and 15 with weaponizing and doing the shellcode smuggling and all that stuff. But we can certainly do that again in the future as part of like a browser exploitation series, because I know a lot of people have been asking for stuff on V8 and Chrome. And, if you go and read the most recent vulnerability disclosures, especially the rare ones that has a walkthrough associated with it, you can see just how complex things have become. And it's still a viable attack surface, but with all the mitigations, like someone was asking earlier, stuff like arbitrary code guard and control flow guard and all these others are pretty much going to be there by default. And then of course you've got a sandbox escape and a privilege escalation into the kernel, like that becomes your exploit chain. Which, as you can imagine, once you get one of those chains together, that's why they're worth hundreds of thousands of dollars, if not getting into seven figures. So, yeah. Cool. I don't see any questions popping up, but you still got a chance to post it. Anything else you want to say about this particular bug, Alexander?
Well, I like it because it's not... Sometimes some bugs you have to go through a lot, like JIT things, shenanigans to trigger it. Here it's a few lines, and I find it quite neat.
yeah, it's always neat when you get one that's not too terribly miserable. What are your thoughts on finding this type of bug for folks who want to go and be able to like hunt for this type of stuff? Because there's obviously the different phases. You got to find a bug, you got to determine if you can weaponize it, if it's potentially exploitable, you got to debug it, you got to deal with the mitigations while you're trying to weaponize it. Like if someone wants to go and find something like this, is it best done via fuzzing or through static analysis, or what do you think?
I guess fuzzing is the better approach. The thing is, so many people are researching V8 because there is a bug bounty, well oiled. They are playing nice, not like some others that say, "Oh no, won't fix," and then they fix it 2 months later, and like what? So a lot of people are researching it, meaning that whenever you find something, usually a RC like that is it lasts for 1 month.
Yeah.
And then it's fixed. Or, well, no. Yeah. Depends who you are when you're using that vulnerability. Let's say it that way. But there are a lot of people looking at it. A lot of people with experience. So it might be frustrating at the beginning. Because what you need to know is that here we are playing with a specific version of V8 that I have downloaded with the Google tooling to download and to compile it. That's it. That takes half a day.
Yeah.
To download and compile, it's super long. So you have to have a pipeline that will do that and then feed that to your further new version and whatnot. So if you are beginning into fuzzing, that might not be the best target. If you are well versed into JavaScript and fuzzing, yeah, maybe. To fuzz JavaScript engine, usually you would use a fuzzer that will produce output based on a grammar. And you need to build that grammar first. And you will find fuzzer like Fuzzily that is super powerful, but you don't have any grammar out there. And that's basically the money maker. Coming up with a great grammar is key here. And time consuming.
Yeah, and I know some other folks have as well, and I've had quite a bit of luck where you take a bug like this, you work with AI, you tell it, this is a bug that was found, here's some other bugs that were found, help me identify a new attack surface potentially within Chrome, for example, or V8. Since you're teaching it bugs that have worked before, it can go and look for other instances of other spots where that same kind of bug may exist, and believe me, it works really well. And having
it's always those kind of let's do something, let's try to redefine a function or add an element in between in a loop or remove it, and this will lead to those type of confusion because the JIT compiler will think that, oh, it's safe to optimize it that way, and whenever you change something, it might not see, oh, this thing has changed, I need to de-optimize it back, and we'll forget about that, and then you have your type for confusion or use after free or whatnot. So the pattern is quite always the same. So using like looking at old bugs, old reports on the monorail of Google, and see those blogs, those patterns, those code patterns that leads to the vulnerability is a good way to maybe train something. Or talking about AI, Project Zero just released a paper talking about finding a stack-based overflow on SQLite using AI. That's 2024 stack-based buffer overflow. That's nice.
Yeah, that's funny. Trying to find schedule real quick that I have for upcoming streams so I don't say anything incorrect, but I am not finding what I want, unfortunately. Actually, okay, I've got a little bit here. So first off, thanks again. Thanks so much, Alexandre. I think that's a great session. I think folks would love to see, obviously, another one, continue to walk through this. Especially with a couple million lines of code. I mean, that's a massive attack surface. So there's still stuff out there for sure. Cool, but like I said before, this particular content that we went through today comes from an update of the SEC760 course coming out in Q1. It's already done. The problem is Hexrays came out with IDA 9, and they completely broke all the plugins with the new API. And so been working with Christian Blickman, or asking like about BinDiff getting updated, and he's been working hard on that, as I'm sure a lot of you know. It's not a small undertaking to get this stuff to work on IDA 9. Some of the stuff is easy, some of it's not so easy. So we have to go and retest everything, which is what's taken so much time. But once that gets done, it'll come out early Q1, hopefully sooner than later. Upcoming streams, I've got, I'm not sure what's going on next Friday. I had someone to come present, but they're unable to do it at that time. So I'm sorting something out there. On Friday, November 15th, I'm actually going to be in Ohio giving a keynote for Hackers Teaching Hackers conference on basically vulnerability research and AI. So I'll be talking a little bit more about that. On the 22nd, I have Foster Nethercott coming on. He's going to be specifically talking about offensive AI. As you all know, there's adversarial AI focusing on the attack surface, which is the machine learning models and such themselves, like testing models and where things can go wrong. But then there's the offensive AI part, which is using AI as a attack aid to improve your skills and the types of things you can do. So he'll be on the 22nd talking about that. And then on the 29th, I've got Hassam from Halborn, a bunch of folks. So there was recently a bounty that was won, I guess you could call it, for $2 million in a Japanese DeFi token. And you know, those bounties in that space, even though the world of crypto and blockchain smart contract cooled down after the crypto winter, that stuff's not going away. I'm sure you've seen Bitcoin going back up again, and there's just a lot of useful technology there. And those bounties are still very large. So, you know, you're doing the web stuff, the web bug bounties, and if you're lucky enough to not get a duplicate finding, usually those bounties aren't very much, hundreds of dollars, maybe thousands if you're lucky. Binary exploitation, you can get some significant bounties, but they're very hard. In the crypto space, looking at Solidity contracts and things like that, if you understand the languages, there's just still a lot of active development going on in that space where security is not part of the build process, and there's opportunity there. And some of those bounties can get, as I just said, into the millions of dollars or hundreds of thousands of dollars. So quite a few folks have been asking for someone to come on and speak to that. Hassam is brilliant. He'll be coming on to talk about that and some specific bugs, and hopefully get you started on looking in that space. And then, of course, we got folks coming in December as well. But that's the end of our stream for today. Thanks, everyone, for joining. And thanks again, Alex. Really appreciate you coming on. We'll maybe continue this one in the future. I'll base that on feedback. I put the Discord link up in the chat if you want to join the Off by One Discord server. There's about 2,000 people there now, which is a great community. And there's a specific channel for stream requests. So if there's a specific topic or a specific guest that you would like to see, you can post it there. And I've had pretty good luck. Thankfully, a lot of people who don't do much public speaking. Well, yeah, I know that, Quad, but we got to use something. But there's a lot of people out there who don't do a lot of public speaking, or just not that often, or don't do it unless it's paid. And fortunately, because I've been doing this channel for a couple of years now, and people see it as a tool to give back to the community. And there's no really marketing or anything here. We just want to educate and help people out. So a lot of people have been appreciative of that and been willing to come on, like getting people like Alyssa Assange on the other week. We had 7,500 viewers, which was a record for this channel at live going on at once. Chompy came on again last Saturday, and she's amazing. Had Yarden Shafir recently. So a lot of great people, and we'll continue to do so. But otherwise, have a great weekend, and we will see you next Friday, and I'll figure out what we're going to be talking about. So thanks, everyone. Thanks.
Thank you.